Okay, good morning, everyone. So it's a great honor for me to here to present our recent work done about how to use generative AI and the large language model to do the seismic design and optimization. And this work is done together by me and my students. Their names are shown on this slider. So my presentation is about 5 parts. So first is about the background and the key concept, why we do the work, and the key knowledge of how to do the work. So currently the design industry is major depends on the human work. So the architecture gives the design plan and engineer do the structure design. So the efficiency is not good enough. And at the same time, because a lot of design data are just stored there and nobody will read it before some retrofitting or other things. So the data usage is also a big problem. And also that the design quality is higher, rely on the engineer's experience. So if some engineers quit or move to other institute, the design quality will be reduced quite a lot. So that is the task we need to address. So yesterday, Professor Lili Xie has given a very good explaining about the difference between intelligence and smart. And I also go to the dictionary and find that, for example, in Oxford language, they said intelligence means the ability to acquire and apply knowledge and skills. So we have a lot of optimization algorithms today, but I think that they are not real-world intelligent algorithms because they don't have the ability to learning. And we want to have some algorithm that can really do the learning by themselves. And why intelligence gets so many attentions in recent years? Because the new algorithm like deep learning, they have the ability to learn the new knowledge. For example, if we give the computer a lot of photos about a dog and a cat, they can identify which one will be dog and which one will be cat. So that this is a typical intelligence performance. And because the deep learning method have a very strong capacity to learning, so if you have more data, the performance of the AI will be better. And with further development of deep learning, and in recent years, the generative AI become a hot word. So before I give my presentation, Professor Nagaya asked me what's the meaning of generative AI. I think this animation shows a very clear explanation about what's the meaning of the generative AI. So you can see there, so these 4 phases are generated by these 4 phases and these phases. So this is computer-generated phases. So this animation clearly shows the 2 characters of generative AI. The first character is that the generative AI means it learns a lot of existing data, and then they can generate a totally new thing. For example, a new picture, or new video, or new text. So that is the first character. And the second character is that the capacity of generative AI is so strong that if I don't tell you before, you can hardly identify this face as real-world people or real-world computer-generated faces. So that is the power of generative AI. So in 2017, when I see this animation, I think, okay, that will be a very big revolution in our design industry. Why? Because the most important design output in our industry is design drawing. But in the eyes of computer, in the computer, no matter you are face generated by AI or a design drawing generated by people or AI, it is just some kind of picture. So if computer can generate a realistic human face, why computer can generate a design drawing that is as good as the real-world design drawing? So that is the fundamental idea of research. So we can let a computer do a lot of learning and generative design drawing that is like the real-world design drawing. And also that we found we still need some optimization because the computer-generated design sometimes have some problem, like the design quality is not so good. And also we're facing the challenge that the AI need to do the drawing, they need a lot of data to do the learning. If the training data is not good, then the generated result will not be good. So we need the optimization to further improve the capacity of generative AI. So then I will first talk about the second will come how about the intelligent design and optimization. So because we need to train the AI, so we need to get a very big training database. So we generate the largest structured design data set in the world. And then we can use this data set to train the AI. And we hire some professional engineers to keep generating new design for the training. And now we have the design algorithm that can do the design for the vertical component, horizontal component layout, cross-sectional design, and some special component design. First, for example, for the vertical component design, because we are talking about earthquake engineering, so shear wall is very important for the seismic design. So we're talking about how to lay out the shear wall. So we propose the algorithm to do the layout shear wall with GAN, GAN, and diffusion models in recent years. And here is two typical examples. So the left two figures are the architectural layout of the building. So the green means wall, the green means window, and the blue means door. And on the right, that is the layout of shear wall generated by AI. So the red one means the shear wall. So can you identify which one is generated by AI and which one is generated by human? Okay, so here is the result. We can see that generally AI can generate a design of the shear wall very close to human design. And in 2019, we use GAN to generate the design. You can still see, okay, some shear walls is not so good. But in this year, we use our new algorithm, and you can see that the generated layout of shear wall is almost identical as the one designed by the human. And also, we can embed the design code into our shear wall design. So we can combine the training drawings and also the training text to guide the final design result. So here is the outcome. So we have some architectural drawing. If we design a building with PGI equal to 0.1 G and design height of 50 meters, the shear wall layout will be like this one. So if we change the height of the wall to 50 meter to 100 meter, the layout will shear wall like this one. And we change the design intensity from 0.1 G to 0.2 G. The layout is like this one. So all this design can be finished in several seconds. So it's very efficient, and you can clearly combine the layout of shear wall with the design conditions. And also we can embed the mechanism into the AI algorithm. So we give a physics estimator inside it. So this is a determinator. It will check the AI design drawing is similar to human or not. And this one will check the mechanics performance or physics performance of the AI design is good or not. And here is the result. We can see that, okay, with this physics embedded, the design is more close to human design, and this can satisfy the design requirement. And after the layout of the vertical component, we can move to the layout of the horizontal component. So typical layout of horizontal component mode is to lay out the frame beams. So we propose, we call the Edge Feature Enhanced GAN, called Grass SF, to lay out the beam. So here is the layout of the columns, and here is the layout of the beam. So you can, I wish you can check which one is, guess which one is done by AI and which one is done by engineer. And here is the result. So AI can generate a layout of frame beams about more than 95%, higher 95%, similar to the human design. And also we can use it for the layout design of beams in shear wall structure. The challenge of this task is that between two shear walls, there is an infinite possibility of layout a beam. So we propose an algorithm to solve the problem. So when we finish the shear wall design, and here is the layout of the beam. So the green lines means the beam. So you can also to guess which one is done by AI and which one is done by engineer. And here is the result. And also we can, after the layout design, we can do the cross-sectional design. So we propose an algorithm called StructGAN knowledge with knowledge and rule embedded. So we input the design condition, the design drawing, and the domain knowledge into the algorithm, and it can generate a design of the cross-section that satisfies both the design condition and also the domain knowledge. So here is the example. So we have the tall building more than 20 stories. The AI design is almost identical with the human design, and AI design can consume 2% less concrete and save a lot of time, can finish the design in seconds. And we do a blind test about 71 tall buildings, and we invite 56 engineers to check, and about 50% of the AI design were judged as engineer design. So we can see that the AI design is very similar to human design. And we can also do it for design for some special component. For example, the seismic isolators. So we can buy the discriminator, physical estimator, and the rule evaluator together to make the design of the isolator satisfy the similarity, the physical performance, and also the design knowledge. And here is the design result. We can see that with this tall building, we lay out the isolator bearing. All the isolator bearing have same diameters, and the arrangement follows the design knowledge. And all the design results satisfying the design code and not too much conservative. And the efficiency is much higher than human design. So after the generation, we go further to do the optimization. So here we use a word we call the intelligent optimization. What's the meaning for the intelligent optimization? That we found our optimization is different from the traditional ways. We're using the big data and let the optimization based on the learning process. So that is the key idea of intelligent optimization. So here is from further explanation. For example, when we do the evaluation of the structural performance or evaluation of the material usage, we can use the intelligent algorithm to make the evaluation very efficient. And also, after the optimization of the design, we will use the optimized result back to our training data set so that the AI algorithm can keep progressing day by day. So this is a key algorithm we are using. We called it a graphic neural network model to represent the whole structure information. So if we have a structure, we have 3 scales of information. For example, the macro scale means the cross-sectional of the beams or walls. The medium scale, for example, the layout, the topological layout of the component. And the macro scale information, for example, the design intensity or the site condition. So we use this graph representation. So the graph edge can represent the macro information. The node and the edge of the graph can represent the topological information of structure. And the global feature of the GN can represent the macro scale information. So with this algorithm, we can represent the entire structure. And then we can use the AI to do the work. For example, we predict the interstory drift. So firstly, we can let AI to generate thousands of design drawings. And then we use these design drawings and combine with the GN. Then we can generate the interstory flexural and shear stiffness. And then we use this one to generate the multi-differential model, and we use this model to do the response prediction. So it can be very quick and very efficient. So here is the result. We can see that with this model, our accuracy is better than existing model, and for the computing efficiency, it is increased more than 100 times. You can finish the interstory drift prediction in 0.5 seconds. And also we can use for the material usage. We use the finite element method to evaluate how much concrete will consume. It will take maybe several minutes. But we use AI, we can generate material consumption in seconds, like a very experienced senior engineer. So we use AI to generate more than 4,000 cases for the training. And also we embedded some domain knowledge for the material consumption estimation. And here is the result. We can see that with our method, our accuracy is better than all the existing models. And with this method, we can predict the material usage, for example, steel consumption or concrete consumption with just 0.13 seconds. So it's very efficient. And then with these 2 ways, we can combine the AI-based seismic response calculation and AI-based material usage evaluation to the evaluation algorithm. And then we can make it very efficient. For example, if we have a structure that can exist the design limitations, and with this AI-powered method, we can finish the optimization in 10 minutes and design satisfying the code requirement. But if we use the traditional way, we need a lot of time to do the fine element analysis, and even we take 2 hours, we still cannot get a good result. So it is very efficient. And furthermore, we can still use this way to improve the design capacity of our AI algorithm. So the AI do the design based on the training data. So if your training data is not good, the AI model will be bad and design result will be bad. But after optimization, the design training data will have high quality, and you have a better model and a better design result. So we use our optimization algorithm to do optimization of more than 300 cases. So with the traditional way, it's very hard to optimize more than 300 buildings. But with our algorithm, we can do it very quickly. And then we can make the AI-generated design result much better with the older training data set. And also we can use this capacity to get some design training data for the real case data. For example, no matter how many data you connected, there always have some design intensity. Maybe the design intensity is so high, it's very difficult to connect such kind of data. So we can use this algorithm to do the work. The fundamental idea is that firstly, we use the generative AI to generate a lot of data. For example, we can increase the data of real classes to more than 7.5 times. And then we can use all the optimization algorithm to improve the quality of this generated data. So you can see that with this algorithm, the performance of this data will be much better. And with this data, we can make the design algorithm better. And then when we finish all the research, we want to use it for the real-world application. So we developed a platform to do the work. So this is what we developed. You can go to the web address, aistruct.com. I think before the end of this month, we will have an English version. Currently, it's a Chinese version. So with this, we called it a Copilot software. You can finish all the data preparation with local CAD software. And when you finish the data pre-process, you upload the data to our cloud design platform, and we do the design and send back the data to the user. So it's very efficient. So now we can finish the design with one architecture journey. We have 3 algorithms to generate different design from the layout of shear wall, beam, component section, material in seconds. And you can see in 1 minute, and you can see that the result is different from each other, but all are original. And also with our algorithm that we just need to 1 click, and we can automatically do the optimization, and it can be finished in 3 minutes, and the structure performance will be much better. And here is a typical example. You can see that after the optimization, all the index of structure satisfying the design code, not only the interstory drift, but all these values. And the material usage of the AI design is close to the human design. And currently, the platform has been used by more than 100 design institutes. And yesterday, I checked it, we have more than 1,007 usage. So when the day before yesterday, when I preparing my slider, I checked this is a recent design outcome. So this is 1,752 design cases of our platform. This case is done in August 12th afternoon. And here is the user design result. We can find that this design result passed the design software evaluation. So this design result can be directly used by the users. And finally, I was talking about our recent work using large language model to make the interaction more conveniently. So currently, the software, we still need some professional requirement for the users to use the software. So we are thinking about how we can make the software more easy to use, that even no professional people can use it. So we use the large language model, LLM, as a controller to control all this operation of the system. For example, for the generation process, we use the prompt engineering of LLM to do the work. So large language model will firstly understand the requirement of the user, and then they will call some functions to do the generation and get the generation result. And similarly, for the optimization, also use large language model to understand what the requirement of the users, and we call the different optimization algorithm, and then generate the optimization result. So here is the totally background of the work. So firstly, we use this like COT reflection or field shot to let large language model to understand the different requirements of engineers. And then we have a knowledge database that we have different algorithms, different components, different objects to combine them together as an agent to serve the requirement of the users. And finally, we transform all the requirements to a JSON format, and the program will execute the JSON format to do the required task. So here is a typical example. So the user first say, okay, we want to have a shear wall structure with this height and with this intensity. And then this large language model will change the requirement to a standard format. And with the standard format, it will generate a JSON file, and they can generate a layout design of the shear wall. And then the user give another requirement. Says, okay, he don't like the shape and don't like the corner layout. Then the large language model will change this requirement to a standard statement. And with the standard requirement, it changes to transform it to a JSON file. And this JSON file will control the algorithm to do the design of this optimization of the shear wall to make the result more reasonable. Okay, so finally is our conclusion. So yesterday, Professor Lili Xie have given a very clear explanation between the first, second, third, and fourth revolution of the technology. And also in some document, like in Dr. Jun Wu's book, they said that energy and information are the two key measures of civilization. So you can see that we coming from the human power to like nuclear power, coming from the bamboo slips to the internet. So that is the development of the civilization. And I think the AI design fully satisfies the two key measures of civilization. The key thing of AI design is that we use electricity instead of manpower to increase the energy efficiency. And you can clearly that will be several orders of magnitude. And also we use this design joining. In all these design joining are just lying in the warehouse or in the library, and nobody will read it. Now AI can make full use it, so that makes the information efficiency by several orders of magnitude. So I think that the AI design is totally follow this requirement, and it should have a very good future, bright future in the coming years. And I'm looking forward that maybe in someday, if we have a good enough generation method, good enough optimization algorithm, we can come into the emergent moment of the intelligent design. So that means that firstly, the AI can do the learning, and after learning, it can generate the design. If the design result is not good, it will optimize it. And after the optimization, the result will come back for the training. So with this all circle, you can see that we don't need a human to involve it. So AI can improve their capacity by themselves. And maybe some days we will see a real world, very powerful AI design tools in the future. Okay, so that's all for my presentation. Thank you very much.